So, how do diesel engines work? Hannah Woolley and Steve Pritchard went to find out more.
I've come to M-Shed on Bristol's Harbourside to talk to Dave Martin and find out more about a historic diesel engine.
Steam was the prevalent motive power for years, and in the 30s experiments were made with diesels and the transmissions got better, because that was always the weak point in the rough world of shunting hundreds of tons of wagons. It's a Ruston shunting locomotive built in Lincoln in 1958 and new to the gas board in Swindon, and in 1982 I persuaded them that they'd like to give it to us. It's 165 horsepower, diesel mechanical, and it works perfectly.
Why does this locomotive have a petrol engine start up?
Because it doesn't have an electric starter, as you might expect, like in a car.
Yeah.
Because it's 6 very large cylinders. It requires a hell of a punch to turn it over to start with.
Why are diesel engines better for shunting than steam or petrol?
The torque on a diesel engine is much better suited to the low revving high loads. That's 165 horsepower, mainline diesels are 2,000 to 3,000 and more.
Dave raised some interesting points. Now I've come to meet Terry Pritchard to learn more about the mechanics of a diesel engine.
You've got an awful lot of torque at 0 revs with a steam engine, but you don't have that with a diesel engine directly coupled or a petrol engine directly coupled.
What's the main difference between a petrol engine and a diesel engine?
So you have spark ignition in the petrol engine and compression ignition in the diesel engine. If you've ever tried to pump your bicycle tyre up, you'll know that the end of the pump where you're compressing the air gets quite warm. You then squirt the diesel fuel into this hot gas, which instantly ignites.
Why is it important to have even fuel injection into the compression chamber?
Well, you're trying to burn the gas in a very uniform fashion. And what you want to do is try and produce a fine mist, and the finer the better, because it mixes with the air and burns much more efficiently. Diesel fuels in very low temperatures used to solidify, and they're called waxing, and modern fuels are less prone to that. Some of the drivers used to have to light a fire under the fuel tank to make sure the diesel was fluid enough to start their engine up, which doesn't sound very safe to me.
No. Why do diesel engines have different numbers of cylinders?
Well, if you're trying to generate a massive amount of power to pull your carriages along, and you try and do it in one cylinder, you have this massive bang and a very jerky action, because the engine has to rotate twice before it can have another bang. So if you have more cylinders, you have more bangs per revolution, and they're smaller bangs, so it's a much smoother generation of power. The downside is it's more expensive.
So diesel trains, as we know them, actually use the diesel to power an electric generator.
The diesel engine, quite a large diesel engine, drives a rather large generator. The electricity is fed in a controlled fashion to motors which are mounted on the axles. And the diesel's got no torque at 0 revs, whereas an electric motor has an awful lot of torque at 0 revs.
Okay.
So you can pull away a 2,000 tonne goods train from 0 revs.
So, what does the future hold for diesel engines? Rod Jenkins is a future fuels expert.
In one respect, we have renewable diesel, and that is the hydrocarbons that we get from the cracking and the hydrogenation of biological sources. And that's only hydrogen and carbon, and its physical properties are very, very similar to that of diesel. Biodiesel, however, is slightly different. We get it generally from vegetable oils, but also from plant oils and fats, where we do a chemical transformation called transesterification.
Could you tell me about the differences between biodiesel, alternative diesel and the normal diesel we use every day?
Well, for diesel, generally the carbon number will be between, say, 8 and 15, and you'll have some cycloalkanes, which just means they make a circle of their molecules. This means that the flash point and the low temperature properties, most importantly, are quite good, and they won't freeze until about minus 20 degrees. Because biodiesel is actually considerably larger, and also because oxygen contributes quite a lot to its intermolecular forces, it'll freeze anywhere between sort of -5 and -10, depending on the actual specific structure of that biodiesel molecule.
And in terms of how the fuels perform, how do they differ?
with the combustion process, all you're actually doing is a very, very exothermic oxidation reaction, which converts pretty much all of the hydrocarbon into carbon dioxide and water. If there's oxygen present in the fuel, you've already done that reaction partially. So the energy density is about 10 to 12% less that of normal diesel fuel, and therefore you get about 10 to 12% less bang for your buck.
And would I have to change how my engine works in any way to use any of these fuels?
If you think about the way that a diesel engine works, where the fuel is sprayed into the combustion chamber, ideally it's meant to finely atomize over the entire combustion chamber and all ignite at the same time. If it's quite viscous, it won't atomize quite as efficiently, and then you'll get these hot spots in the combustion chamber where that can lead to sort of knocking, where you actually get two separate explosions in your combustion chamber that knock against each other, and that can really, really damage your engine. Any diesel that you actually buy is blended with 5% biodiesel. The problem is that ideally with any biofuel we want to get away completely from using any fossil fuels. However, the technical problems that we actually have from them are something that we have to overcome using research. Whether or not we'll actually be able to do this, that's another question.
We can look forward to seeing diesel engines on our railways for many years to come.